a thumbs up if you're doing okay, if you're enjoying your Sunday, if you're enjoying your weekend. Just a thumbs up if you're doing fine. I'll get my thumbs up going in there. Anybody else? Asani, you're not doing good. See Andrea, Zach is doing good. Okay, great. All right, so see what Roderick is saying in the chat. Roderick saying he doesn't know how to give a thumbs up. Roderick, you just put the cursor in the chat bar, you bring up your emojis on your keyboard, and you press the thumbs up. And you press send. That's how you do that. All right, I see the thumbs up rolling in. So I'm glad to know that everybody is doing good. Glad to see that persons have returned from our last meeting. Normally our agenda is to start with a bit of aviation news, and we go into club news, and then I'll introduce our presenter for today, and we'll get into our presentation. So aviation news, we get to understand that the Boeing 737 MAX has finally been green lighted to do a test or certification flight. That flight is gonna be this Monday, and we're hoping for some great news out of that, because as you guys know right now, aviation has taken a big hit because of COVID-19 and all that is going on in the world with the pilots being laid off. We see that I believe Emirates are one of those airlines in the Middle East have laid off quite a few pilots. We also see where Liat has liquidated, and they are now forming a new company. So some good news from the 737 MAX test flight will be something great for aviation. So looking forward to seeing what is gonna come of that this coming Monday. That's one. Another news that's coming out of the Middle East is where 100+ pilots have been grounded, because we see where a lot of them are with fake licenses. So coming out of that investigation of the Airbus that crashed in India, I believe, or in one of those Middle East countries, that's one of the developments coming out of that crash, where we see that a number of the pilots actually don't have proper qualifications, or they don't have real licenses. It is not clear if the pilots that were flying the actual aircraft, the actual accident aircraft, are one of those pilots. But I mean, the more the developments come out, the more we'll get to understand. So that's it for aviation news.
Richard, the country is Pakistan.
Pakistan, great, thanks. So Pakistan has a lot going on right now. So we'll see as time passes what's gonna come out of that. So those are the major happenings over the past 2 weeks where aviation in the world is concerned. Now, for club news, you guys would have seen, if you're following our Instagram, where we posted a picture of our engine that was being installed on our Cessna 152. Now, there's still a little bit of work to be done, but the engine being installed is a major milestone in getting our aircraft back up and running. We expect to have that done by the ending of mid to the ending of July. So we just want you guys to stay tuned to our various social media for updates on how our airplane is doing. Another thing that I wanted to mention is that the next club meeting, which let me grab my calendar, the next club meeting, which would have been the 12th of July, is now going to be on the 26th of July. So we've been going for 6 months strong, and we're going to take a small break on the 12th of July, and then all being well, we'll come back, fresh minds, fresh everything for the 26th of July. Hopefully we'll have a great presentation. I won't mention the name of the person, but hopefully we'll have a great presentation from an airline pilot ready and waiting to go for you guys and return on the 26th of July. So, and the final piece of club news that we have is the return of physical club meetings. Now, for physical club meetings, we don't have a concrete date yet, but what we're looking to do is open back the facility for physical visits. So you guys would have known earlier on in this year, up until March when the lockdowns happened, persons would have been able to come down to Tinsipen whenever they so choose, to just hang out for the day, or come in and we'd have club meetings done by Tinsipen. So now we're opening back up for persons to come down and hang out for the day. Now, you're going to have to call in and let us know prior to you coming down. But as of now, what we're doing is we're making a facility available to persons once more for them to come down and chill. And I know a lot of persons come down on a Saturday just to hang out for the day and be immersed in the environment. So that's something that we're now making available to all of our club members once more. So that would have concluded the news that I have for you guys today. Now, that being said, I want to get into our presentation for today. So today we have actually a presenter that is returning for the second time. The last presenter we had was Zachary Parchment, and he was so kind to volunteer to give us a follow-up presentation, because there are such great reviews for the last presentation that he did. So Zachary is back today. Zachary has put together a nice presentation on complex airplanes for us today. And Zachary, we're looking forward to hearing what you have to say, definitely. So without further ado, I'd like to invite Zachary on, just to introduce himself and to get into his presentation for the day.
Hello, I am Zachary Parchment. As you guys would have known from like the last time, I'm just a commercial pilot with the multi-engine rating, and I'm here to present on complex airplanes. And this won't be a really long presentation because it's not that much to cover, but it should be short and good.
Great. Guys, just want you to know that I don't want you guys to be shy. You guys can chime in. You guys can ask your questions. Right, we want this to be as discussional, or we want it to be discussion based as possible. So feel free to chime in as always, and let's just have a great chit chat with a topic, basically. All right, so Zachary, you can go ahead.
Yeah, all right. Can everyone see my screen?
Yes, they're seeing your screen, Zach.
All right. So, we're presenting on complex airplanes today. So, is there anyone in the chat that might have a good idea what is a complex airplane or what it might comprise of? And as Richard said, like, don't be afraid to speak or answer. You know. All right, so let's get to the definition. So this is a definition from the FAA, where a complex airplane is just an airplane that has a retractable landing gear, flaps, and a controllable pitch propeller. In lieu of a controllable pitch propeller, the aircraft could also have an engine control system consisting of a digital computer and associated accessories for controlling the engine and the propeller. So basically, a complex airplane, according to the FAA, is just flaps, retractable landing gear, constant speed propeller, and a FADEC engine, right? So basically, computer controls the operation of the engine instead of you controlling the manifold, the prop, and the mixture. So the first thing we'll get into is the flaps. So I reckon a lot of people here probably know already flaps on the airplane, but basically flaps are, or a good definition, airplanes can be designed to fly through a wide range of airspeeds. Many compromises are often made by designers to provide for high-speed cruise flight and low speeds for landing. Flaps are a common design effort to increase the airfoil's camber and the wing surface for lower speed flights. Flaps work primarily by changing the camber of the airfoil, which increases the wing's lift coefficient, and with some flap designs, the surface area of the wing is also increased. So basically, the advantages of flaps, you can produce more lift, giving you lower takeoff and landing speeds. You can produce more drag, allowing a steeper descent angle without increasing your airspeed on landing. You can reduce the length of your takeoff and landing roll also by using flaps. So basically, using flaps just ensures or allows the airplane to develop more lift and fly while flying at slower speeds. So generally, during takeoff and landings, depending on the weight for takeoff, the aircraft might use flaps for takeoff. And why this is done is to basically get airborne faster at slower speed. And is everyone understanding like the use of flaps, the purpose of flaps?
Yes.
That's a yes for everyone. So now I just got the 4 basic types of flaps right here. Plain flaps, the split flaps, slotted, and the Fowler flaps. So depending on the airplane that you might fly, like for a good example, the Cessna would have plain flaps. And another example could be let's say a 747, which would have a Fowler flaps type design. All right, so that was it for flaps. Let's speak a bit about. All right.
Can you elaborate on? So I understand you have flaps at the back. Can you elaborate on the flaps on the leading edge of the plane, the slats? Like, what are their purpose?
I think there's an airline pilot in this meeting that could probably elaborate more on the slats.
Right. Demar.
Hey guys, how's it going?
Yeah.
Going good, going good.
All right, so you wanted me to talk about the slats.
Mm-hmm.
So the slats, there's simple airplanes out there. On a complicated airplane like we control the movement of the leading edge, so that's why they're called slats. But on some airplanes, less complex, they have a fixed device on the front, which is called a slot. And all that does is it increases the airflow over the wing as you change the angle of attack. So it allows for, in simplest terms, it allows for you to have a higher pitch up attitude when you're coming in. So like, say you're in a CRJ, they don't have any leading edge devices. If you notice that when they're coming in on approach with just the trailing edge flaps on them, they have a very nose down attitude approaching the airplane, the airport. So they need to keep that nose down attitude in order to keep that high airflow over the wing. Whereas with the Airbus A320, when it's coming in, you'll see a much more nose up attitude because the leading edge device allows for the airflow to be increased over the wing as you increase the flaps at the trailing edge of the wing, if that makes sense.
Okay, so do they delay the critical angle of attack? Is that what they're doing?
They do. They absolutely do, and it will help in terms of decreasing your stall speed.
So like when we're in landing configuration, you're already at a high angle of attack, so they aid you there.
Exactly. And it also provides for much more controlled airflow at the back of the wing because you have higher speed air that's flowing over the wing due to the air that's allowed to flow over the wing.
Is that due to
The
Venturi
slot
effect?
that's created. It's that too, but also just from the airflow that comes up naturally underneath the wing as you increase the slats at the front. Yeah. So on the Airbus, we actually have, it is a more automated airplane. So we have flap 1, which on the ground is
1 plus F. 1 plus
exactly.
F. And then in the air, 1 only puts leading edge slats, and then 2 gives you flaps.
Yeah, but the thing is as well, with the Airbus, if you get above 210 knots on all of them, 319, 20, and 21, the flaps automatically retract. So above a higher speed, you don't need that. You don't need the flap portion of the 1 plus F anymore. So it automatically retracts.
So the Airbus automatically knows when to retract the flaps, but it doesn't do that with the slats, right?
No, the slats won't come out. If you get below a certain speed, which you wouldn't be able to get below a certain speed in the air for this to happen, believe it's 100 and something knots. I'd have to double check.
And then alpha floor kick in?
Before alpha floor, because this would be a very, very slow speed. The flaps would automatically come back, would automatically go back to the 1 position.
Oh, does that happen in direct on alternate law too?
With the changing of configuration, the changing of configuration is separate from the flight laws. So we always operate in normal law, but in alternate law, I believe it would be the same, but I'd have to double check.
Oh, okay. Right. Well, I never knew the Airbus was that advanced.
It's a great machine, as everyone knows. Airbus is the best aircraft manufacturer out there.
Yeah, it really is.
I don't know. Does that answer the question there with the slats for you guys?
I understand it.
Anyone want clarification on anything?
So one thing you said is a CRJ doesn't have them, so they have to keep a nose down attitude on final because.
Well, it naturally will have a nose down attitude, right? So on some of these bigger airplanes, like I flew a lot of props in my life before getting onto a jet. So on the C-130J Hercules as well, we had just trailing edge devices, no leading edge. When you put that flap in, you can see your attitude is automatically based on that natural camber that happens with the wing. You're going to be a little bit more nose down, correct?
Oh.
Right? So like if you didn't trim an aircraft, you put flaps in, you're naturally going to have a more nose down attitude. When you now introduce the leading edge devices, you're naturally going to have more of a nose up attitude, right? And you're going to be changing now the airflow. So if you look at it in terms of your angle of attack, where the wind is coming from as you're flying through the air, if you have a more of a nose down attitude, it's going to change where and how the wind is affecting the airplane, which is where it's going to change the angle of attack. So in order to have, I guess, like with the Airbus and other large airplanes, in order to lower the speeds so you can fly slower and to decrease the angle of attack as you're coming in on approach, you have a leading edge device.
Oh, I see.
Yeah. Does that make sense? As well, with a lot of the big jets, I don't think Zach mentioned this, but with a lot of the big jets as well, you do want to have the final flap or some sort of intermediate flap to increase the drag as well, because on our jet engines, and the bigger the jet engines get, you need to have a higher spool. And then that higher spool allows the power to come in a lot more instantaneously when you need it. So when we put our final flap, you can even hear it. We're needing about, depending on the weight, we're going to need that much more of an increase in power. And that's on purpose for jets. If you look at a 747, you can see the inner flaps are they're very, very high angle. And that's on purpose to help increase the drag profile of the airplane. So then in turn, you're getting a lot higher N1 speed. so that you have a lot more spool on the aircraft, so that in case of a go around, you don't have that excessive spool time.
Oh, because they're not instant power with the turbine engines, so you have to.
Exactly, because even like when you take off in an airplane, and sorry, I'm going to stop talking here for a second. When you take off in an airplane, for us, our procedure at Air Canada, before, when we're lining up on the runway, we go up to 50% and we stop there. And you can hear, when you're a passenger to the airplane, you can hear the engines actually taking their time to spool up. That's not us taking our time and spooling it there. I literally, when I'm in the airplane, I stand them up at 50%. It's like a 1 second movement to 50%. But then the airplane takes time. That's how long it takes for those engines to spool. So if, yeah, go ahead.
Oh wait, so is there no way to get it to go faster? That's just how the engines are limited.
That's how the engines are, because you're spinning, you get into that whole jet engine theory. You're spinning this device with a very big fan at the front, right? So you need to move a lot of air before that fan start, because it's all free, right? They're not, some of these parts aren't all connected, right? So you're spending a lot of air in order to get that big fan spinning at the right speed. Once it's at 50%, the travel to whatever your takeoff setting is a lot quicker. So some of the flap is also designed for drag to help with the spool as you're coming in for approach. If you need to do a go around, then the power is a lot more instantaneous, as opposed to a prop where as soon as you apply the power is there, right?
Oh, I see. Thank you.
So that was a there's a very detailed response. Thanks for that, Demar. Love it when our professionals get involved with our meetings. I see where Amri Hansen has his hand raised.
Yes,
Amri, you can go ahead and ask a question.
Yes, I have a question about the different types of flaps. Could you please elaborate on them, especially the Fowler flap?
Zach, if you go back a slide, so we to the right. So yeah, Zach, you could take it away if you want.
All right, so basically on the different types of flaps, I'm not sure if I have the best answer to elaborate on each one of them. I just know that basically with the plane flaps, it's the length, the difference, the distance between the trailing edge and the leading edge of the wing. It's still the same, just the how would you say, the shape, the dimension of the wing has changed with the plane flap. So what that does is it increases the lift and also increases the amount of drag on the airplane for you to fly slower. I don't know if that makes sense. Does that make sense to you?
Yeah, I understand that one.
The split flap, I'm going to be honest with you, I'm not exactly sure how it works. I've never even seen an airplane with it. I'm not sure if anyone else could elaborate on that one. Anyone
So my basic understanding of these different types of flaps, and sometimes there's exceptions to these rules, but you wouldn't really see a split flap on a very high powered jet or something with a very clean profile, because as you start to get into airplanes that go a lot faster, you want to reduce the amount of parasite drag. Is everyone familiar with what parasite drag is?
A-firm.
So you want to reduce, so you want to keep the profile as clean as possible. With the split flap, you do get that airflow, but you're losing a lot of efficiency over the end, but it is a simpler device. You will get some high lift from it, and there will be some airflow that's going to go in between the flap and the wing, but it's not the cleanest setup as compared to like a plane flap, which is just pivoting. The slotted flap is almost like a slat as well, or a slot, in that you do have that airflow. So it's like an airfoil within an airfoil. But the thing is, it's not increasing the from the fore and aft, the length of the wing. Whereas now your fowler flap, you'll see on most of the bigger airplanes in that you do have that slot component as well. So you do have a secondary airfoil so that you have as much efficiency in terms of that device maintaining its lift. And then you're also increasing the surface area of the wing. So you're able now to have a profile that's a lot more versatile. So you look at like the Airbus A320. I speak of that because that's what I fly. You have something now that's able to do Mach 80, but then in our lightest configuration we can land at 120 knots. A lot of that is due to that flap design and the different types based on the profile. If it's a faster jet and you want it to be able to do those higher speeds, and then also be versatile in the slower speeds, you want something that can kind of clean up the airfoil a bit and is efficient in terms of its deployment.
Yeah, so that was a really good explanation. Like, I almost forgot I was presenting because I just like to listen when he speaks that often. So, thank you. Thank you much for that. Do you have any more questions on flaps? Whoever asked a question.
All right, thank
All right, so let's get.
I'm all right, thanks.
All right, let's get into the constant speed propeller. So, could anyone give me their explanation as to what is a constant speed propeller or controllable pitch or variable pitch, whatever you like to call it?
I would like to take a shot at it.
Yeah.
So, from my understanding, a constant speed or variable pitch or whatever you want to call it, a prop that can change its pitch angle is pretty much, as the name states, constant speed, where you can change the deflection of the prop to maintain a fixed RPM. So, for example, you have aircraft that have these constant speed props have a better efficiency in different flight phases. So, just to go back to a fixed pitch prop, you'd only have maximum efficiency in a number of flight phases. Let's say you have one that's good for climbing. You'll only have great efficiency in climbing, but then in your cruise, you'd suffer a bit where efficiency of the prop is concerned. So with a constant speed prop, you basically can change the pitch of the prop to suit all phases of flight. So you'd have a pitch setting for takeoff. You'd have a pitch setting for cruise. You'd have a pitch setting for landing configuration. Just to it helps with efficiency. Now, this pitch is maintained even though you can change the power setting of the engine. So normally for the fixed pitch prop, you would have a prop control and you'd have power control. So the power controls the manifold pressure of the engine, and the pitch, the prop pitch control would control the RPM. So that's my basic understanding of it.
Yeah, that's basically exactly right. So basically a constant speed propeller, basically a propeller that is designed to automatically change its blade pitch to allow it to maintain a constant RPM. Now you might be wondering, automatically, we'll get into that. Irrespective of the amount of engine torque being produced, or the airspeed or the altitude at which the aircraft is flying, is accomplished by the means of the constant speed unit or the prop governor. So basically, how it maintains that RPM if you're going to a climb, descent, or cruise flight is through the prop governor. The constant speed propeller keeps the blade angle adjusted for maximum efficiency for the most conditions of flight. So pilot controls the engine revolutions per minute indirectly by means of the prop control, which is usually the blue lever in a complex airplane, which is connected to the propeller governor. For maximum takeoff power, the prop control is moved all the way forward to the low pitch, high RPM position, and the throttle is moved forward to the maximum allowable manifold pressure. So this might not make much sense at the moment. So I'm going to draw a prop and try my best to explain what's happening here. Right? So I'm going to draw a little prop system. It might take me a minute. All right, so the first thing I drew was the propeller blade itself, right? So this in front is called the prop hub. And what I'm going to put in it is a little thing indicating nitrogen, which is N2. And I'm going to put in a mechanical spring. And I will explain why these things are there. Can you see the screen, huh?
Yep, yeah, I can.
All right. So I have N2 in the prop hub, and a mechanical spring, a propeller, and now we're going to draw some lines. All right, so this last thing that I just drew, it's called a pitot valve, pilot valve, sorry. And I will explain how this whole system works, because it's one thing to just say, oh, the blade angle changes, but how does it change? So this is how I'm going to explain how exactly it changes. You guys would excuse my penmanship, it's not the best. All right, so can everyone see this, right? All right.
Mm-hmm. Yep.
So,
Yeah, I can.
all right, so basically, there is a blue, there's a blue lever in the cockpit, which is the prop lever. This is indicated at the top, right? So what happens, when with a constant speed propeller, you have different conditions. So I'm going to explain controllable pitch first, all right? So controllable pitch means that you can change the blade angle of the propeller. How is this done? You move the prop lever either forward or back. So I want to show you what happens when you move the prop lever forward. So what happens when you move this prop lever forward, the spring, this thing right here called the speeder spring, right, which is this right here, what happens is that it expands. So basically the speeder spring expands and this pilot valve, it moves down. It moves down, and so that the oil from the oil sump can go into the prop hub. And what that does, it increases the blade angle. So when you move that prop lever forward, the pilot valve goes down, it lets more oil into the prop hub, decreasing the pitch angle, which also gives you more RPM. So in a simplified way, basically when you have props forward, you have more oil, you have more RPM, and you have a lower pitch. So basically for takeoff, you will always have the props forward because you get more RPM from a lower pitch setting and you have the most oil in the prop hub. Does this make sense? Does everyone kind of understand what happens when you move the prop forward?
No, no, I'm a bit confused.
Yeah, go again one time. You kind of lost me as well.
Yes. All right. I'm gonna try to explain this a little bit clearer. All right. So you have the prop lever, right?
When you say push the propeller forward, you mean the entire thing?
When you move the prop lever, which is the blue lever, forward, right? Like as if you're moving the throttle forward for takeoff. When you move the prop lever forward, what happens is this speeder spring right here, this spring, it expands, forcing this pilot valve to move down. You get it?
Yes.
So when this pilot valve moves down, it allows more oil from the sump to go into the prop hub. And that's what changes the blade angle.
Okay, I see.
So when more oil enters the prop hub, the pitch, the blade angle is changed to less. Like, so basically when you go prop forward, what exactly happens is you have more oil that enters the prop hub, which gives you more RPM from the engine and a lower pitch angle, less pitch. You understand?
Yes.
Yeah, so basically where you store oil in the airplane, basically that oil goes into the prop hub, changing the angle of that blade, which in turn gives you less or more RPM depending on where you set your propeller lever, which also indicates the amount of oil or less amount of oil that will be present in the prop hub at the time.
Wait, and
so basically
the change in RPM is because of the angle of the blade, right? So because the blade angle changes, it causes the RPM to change.
Yeah, so basically, if you have props pull forward, then you're getting the most amount of RPM capable from your engine, you know. And if you bring your prop lever back, oil is removed from the prop hub. So basically, let me explain prop back, right? So just like how we have prop forward, where this spring right here, it expands and forces the pilot valve here down, it's the opposite. When you bring the prop lever back, this spring contracts and it forces the pilot valve to go up, releasing oil from that prop hub. So let me clear up the screen and kind of guide you through that. Yeah, so when you go prop back, right? So you're bringing that blue lever back down. This spring right here, it contracts. So it contracts together and it brings that pilot valve right here. It forces it upward. When this pilot valve goes up, then the oil from the prop hub, which is keeping that low pitch angle, it brings the oil back into the oil sump, right? This increases the pitch angle. So basically when you have those prop back, when you have prop back, what that does, you have less oil in your prop hub. You're going to also receive less RPM and you're going to have a greater pitch angle. You understand?
Yes, I understand.
I have a question.
Yeah.
All right. So if I pull the RPMs back, say I'm at 2000 RPM, I pull on the blue lever until it's at 1800 RPM. The governor is what would keep it there, right?
Yes, I'm going to get into the governor. I'm going to get into the governor.
Oh, okay, wait. But my question, another question I don't know, right? So when I pull it back to 1800 RPM, does it change the engine speed or does it, what does it do? It's moving that spring and then the blade changes to get to take the most air at 1800 RPM?
I don't think I understand. Could you go again?
So say I bring it back to 1800 RPM for climb out, right?
Mm-hmm.
Is it my whole engine that is reducing its speed?
I really don't understand like what you're trying to ask. I don't get it.
I don't know how to word it. It's just the blade angle that I'm changing, right?
Yeah, you're changing the blade angle.
And that alone?
in
So
terms of bringing.
I think you're asking about the internal parts of the engine versus the prop. So it could be a case where the engine is turning over at maybe 2,500 RPM, but the prop has more RPM. That's what you're asking, Jaffe?
Kind of, yeah.
I'm not sure the best way to answer your question, reckoning to the point that I'm not fully understanding what you might ask. But like when I get through all of this, maybe it might make more sense.
All right.
And maybe I might indirectly answer your question.
Yeah.
Yeah. So does everyone understand what I mean by like prop forward and prop back? Like what happens in the system? Right. So basically the oil goes from the sump, goes through the pump, and then either if you bring your RPM forward or back, let's say we bring it forward, it lets more oil into the prop hub, decreasing that pitch, giving you more RPM. Does that make sense?
Just to confirm, when you say prop forward, you don't actually mean that the prop itself is moving in a forward direction. You mean the angle of the blade is changing.
Yeah,
So,
just the angle is changing. So basically when you move your propeller lever, that lever, when you bring it forward, right? Basically what happens is just it lets more oil into the prop hub, and that decreases the pitch angle and gives you more RPM from the engine. And then I show you how that happened with the speeder spring basically expanding, bringing the pilot valve down and letting that oil in. That's how the pitch angle is changed.
I have something. Wait, so how? All right, here's a better way of wording it. So if I bring the prop lever back, right, I'm kind of biting more air, right, with that propeller.
If you bring it back,
yeah,
or forward,
back, like I pull it back towards me, the blue lever. Am I in a way biting more air? Am I getting a bigger pitch? Like
when you bring it back, yeah, you're getting that. You increase the pitch. You increase the pitch angle of the propeller when you.
And is the reason the RPMs slow down is because you need more torque now to spin it with that configuration?
That's a good question. Actually, not sure the answer.
Yes, that's correct. So the reason, okay, so if you look at it like, sorry Zach, I don't want to disrupt your presentation here.
You're the best for explaining these things.
No, I'm not the best. I promise. There's better, but the thing is, okay, so if you look at it where everything stays the same. So say you're doing 2000 RPM, you don't touch the power, you don't touch anything. If you move the prop lever forward, your RPM has to increase on the prop. So if now for the same amount of power that you have, power setting that you have on the engine, for the RPM to increase, the propeller needs to spin more freely. The only way that the propeller can spin more freely is if it's biting less air. Does that make sense?
Yeah, it does.
So and when you move the power back, when you move the propeller back and you keep the power the same and the RPM is decreasing, so it needs to be harder to spin. So when it's harder for it to spin, the blade angle has to increase. It's harder for it to turn in the air. Does that make sense?
Mm-hmm.
So as you're moving and you're moving oil, you know what? There's a lot of bright people in here. The oil thing was always confusing to me. But as you're moving stuff in and out of the prop hub to increase and decrease the pitch of the blade, all you have to remember is that if you keep everything the same and you move it back, it's harder for it to spin. If you take a windmill and it's harder for it to spin, that means that the angle on the windmill is just a lot bigger. If it's easier to spin, the angle on windmill is a lot smaller. Does that make sense?
Mm-hmm.
So at a high RPM, like on props, when I used to fly the Q400, when we flew the Q400, it was like these props were literally like speed brakes. If we're coming in and we're fast, we push the props all the way forward. That's the most drag configuration. The blades are spinning fast, but they're creating that much more drag on the airframe.
Because they're moving less air now.
Exactly. Make sense?
Mm-hmm. So me pulling back on the lever makes it take a bigger bite of air, reducing the speed because it has to try harder now.
Exactly.
Oh, I see. Okay.
Exactly.
So-
That's the way I always remembered it.
This is not affecting my engine, like let's say it's a combustion engine. That's not affecting that, right?
So the thing is, when you say that, now you get into more complex systems. There are fixed shaft propellers, and then there's free turbines, right? So it depends. Like what I'm speaking from was a free turbine. So the prop and the NG speed were two separate. So yes, they're gonna affect each other, but it's gonna have less effect than if it's a fixed shaft all the way through the engine. So that question changes depending on the type of engine that you're dealing with.
Okay.
So when you're taking off, the propeller is always going to be back, right?
No, when you're taking off, you're going to have it at the maximum RPM. So it has a lot of power, but it's creating a lot of drag as well. And then how we flew the
So that's when the
Q400 was.
angle is forward.
What do you mean by forward? The
So there's a greater angle.
If the propeller is spinning faster, then it's the angle in terms of its relative angle to the air is less. That's how you have to look at its relative angle to how much air it's biting is less. If the propeller is spinning slower, the relative angle of the prop to the air is more.
Okay, thank you.
And when the relative angle to the prop is more, it's almost like you're feathered, right? We talked about feathered engine. When you're feathered, you're not producing thrust, right? So does that make sense?
Yes, yeah, I'm
okay.
I'm understanding now.
So when you're feathered, yes, you're aerodynamically more clean, but you're not producing more thrust. Whereas when you're spinning faster, your relative angle is smaller, so your relative angle is smaller. It's easier for the prop to spin, but drag wise, there's a lot more drag.
So like the prop lever is kind of like the gears in a car.
Yeah, exactly.
So like a fixed pitch would be like a car stuck in third gear. Well,
always stuck in third gear. And the thing is too, if you ever drove, that's a perfect example. If you ever drove a car that's stuck in gear, you know, when you drive a 4-speed and it really should be a 5-speed or a 6-speed, you know, you get fast and it just, as you're getting fast, you're now having that same effect on the engine. You hear it wanting to rev more and more and more. You're going downhill, it's revving fast. You go uphill, it's revving slower. That's kind of the same thing. Whereas now with a constant speed propeller, you can alter the gear as you go uphill, downhill, and the wind speed as you go faster is not going to necessarily change the speed that the prop is spinning.
oh,
Okay, I see. All right, thank you.
Anyway, sorry, man.
Love it. Zach.
Yeah.
Zach, back to you.
Yeah, so could, like, just to make sure that at least someone understands, could someone explain what happens when you bring the prop lever forward from what I said? I'll give it a shot.
So I want to try at it, but I'm gonna need some help. So
Yeah.
all right. So I want to say the steps, and then you guys just fill in whatever I'm missing out. So when I move my prop lever forward, what does the speeder spring do?
So basically, the speeder spring, which is the spring that is basically connected to the prop lever, it expands.
So the speeder, so the speeder spring expands when I move my prop control lever forward. I want to say that that allows oil to flow forward into is it the prop governor?
All right, so you missed one thing. So you missed one thing. So basically, when that speeder spring expands more, right? This pilot valve, you see a little arrow that goes like toward the propeller, right? Which is right here.
Right at the top.
Yeah, so basically that pilot valve, it moves down to where this arrow becomes right here, which lets that oil into the prop up.
So basically, like when I turn my shower on, the valve opens and that allows water to flow.
Yeah. So basically, so the pilot valve, it goes down, which allows oil to go into the prop up, which decreases the pitch angle.
Right.
Make sense?
So so when you say decreases the pitch angle, pretty much that means the face of the prop is more flat as opposed to having a greater angle.
That's like very relative compared to like how the prop was made, like, you know, the design of the prop.
Okay.
But,
All right, cool.
But yeah, that's what happens, and you can give the same explanation with the prop back. So you could come and try again, and what happens when you go bring your props backward.
Okay, so with moving the prop back, naturally you're gonna move the prop lever back to you. So moving the prop forward, you push it up. When you're moving the prop back, you
like
pulling
almost like
you're pulling the blue lever back towards your chest, basically. Right? So in pulling the prop lever back, the speeder spring contracts.
Yes, it contracts.
Right? And then I forgot the name of that fancy valve, but you're right, it's in my face. Pilot valve. So that basically from what I'm seeing on this diagram, you'd have a back and forth motion. So when you push the prop forward, the valve at the top would go downward, and then this arrow now, the back arrow that you have underlined here, would go down. When you pull the prop back, the opposite happens, where the valve goes up, and that allows that valve goes up, and that allows oil to flow in the opposite direction, causing the reverse effect on the prop. So that would make the prop get more of a angular type of deflection, if you will.
Yeah, more pitch, perfectly right. So basically, when that pilot valve goes up, the prop comes out. What helps that oil to come out and increase the pitch angle is where the nitrogen gas and the mechanical spring right here, that helps to force the oil out back into the sump, right? So when you bring that prop lever back, and that's basically what happens when you bring that prop lever forward and back. It's like a repetitive motion in like moving that lever. So the next thing I want to speak about now is the governor. All right, so this line that I have right here in green, this is just like indicating the prop governor, right? So this whole system of the flyweight and the speeder spring and the flywheel is all incorporated inside of what we call a prop governor. So what happens when you have a prop governor, right? So in a fixed pitch propeller airplane, what you would normally notice is that if you have the RPM setting set at like 2300 RPM, you're cruising, right? And let's say you should pitch up, that RPM is going to bleed off, right? Because there's not as much airflow going over the surface, over the surface. And if you should pitch down, that RPM is going to increase. Why? Because the opposite happens, because you have a lot more airflow. In a constant speed propeller, no matter if you pitch up or pitch down or cruising, that RPM is going to remain the same. And what causes it to remain the same? The prop governor. So how does that work? All right, let me show you, I'll give you the best example of how that works. So with a prop governor, right, you have two conditions, called the overspeed and the underspeed condition. So I'm going to explain the overspeed, right? So overspeed, as you might imagine, just with a fixed pitch propeller, when you pitch the nose down, the RPM is going to increase even without you adjusting the RPM setting, right? So we call that overspeed. And how does the governor account for this? So what happens is, remember I said that everything inside this governor right here. So what happens, this flywheel is directly connected to the propeller of the airplane. So when you pitch down and that propeller wants to spin faster, what happens is, because it's connected to the flywheel, it generates more centrifugal force inside that prop governor. So when when there is more centrifugal force, what happens is these flyweights they come apart. So this flyweight right here. So I'm going to draw the same thing down here. So as they are right here, what happens is they end up like coming apart. You kind of understand what I'm trying to do here? Like it turns away from each other more. Does this make sense so far? Anyone?
Yeah, it does to me.
Yeah, that's good for me.
Yeah. So basically, when you have that overspeed condition, and because the propeller is trying to the flywheel, it generates more centrifugal force inside the governor, and it causes the flyweights to want to kind of leave each other, like expand from each other. And what happens is similar to when explaining prop forward and prop back, right? When it wants to overspeed, what happens is the speeder spring, when the flyweights expand from each other, the speeder spring contracts. I remember what happens when the speeder spring contracts. The pilot valve goes up and it removes oil from the prop hub, right? So basically, when the propeller wants to overspeed, the centrifugal force makes the flyweights go away from each other. The speeder spring, it contracts, forcing the pilot valve to go up. Sorry, expand. Contracts, forcing the pilot valve to go up and bringing that oil from the prop hub back into the oil sump. Does that make sense?
Mhm.
Does it make
Yes,
sense
it
to
does.
everyone?
Wait, so
Have I
that's
explained it
how
well?
it works automatically. That's what you're saying.
Yes, it does it automatically, but due to centrifugal force.
So are there planes that don't have that, where you have? Are there planes where you can change the pitch angle, but it doesn't do it automatically? You have to manually use the prop
Yeah,
lever.
any plane that doesn't have a governor to like automate that process, you would have to do it yourself.
But I have a question.
So wait, even if you have a governor, can you still manually use the prop lever?
Yeah, for sure.
Okay.
I have a question. So I'm cruising at 100 knots indicated, like 3,000 feet, 1,800 RPM selected on the prop lever, and then I pull the power lever back a bit. What will happen? Will the blade angle change to be able to do 1,800 RPM at that power setting with the amount of torque the engine is providing there?
Basically. So what I'm getting from what you're saying is you're moving the manifold pressure.
Yeah, I'm changing
back,
the
right?
manifold pressure to a lesser amount.
Yeah. So basically, you have less power in the cylinder. So the governor will help the propeller to find a pitch that will maintain that RPM that you
For
were
that
at
given condition.
for the condition. Make sense?
Oh, yeah, I understand that so good now. Thank you.
Yeah. So basically, before we even fly, we have like a test. We have a prop cycle and a governor test. So basically, the main thing that we're looking for in a prop cycle test is you want to look for like at least in the smaller airplanes. I can't speak to the jets. You can go back to them more about the jets. So basically, we're looking for a drop in oil pressure. Like this is just testing that the whole system is working. So we're looking for a drop in oil pressure. We're looking for a drop in RPM, and we're looking for an increase in manifold pressure. So that's basically a prop cycle test. It's just bringing that prop lever down and up like 3 different times, looking for these changes on the instruments. Does that make sense?
The prop lever can affect the manifold pressure?
Yeah.
How?
Maybe the market could explain this one better than I could. Is Demar here?
Sorry, what was the question?
He was saying. Oh yeah, you go. You explain it.
Yeah, I was explaining that in the prop cycle, where we're usually looking for 3 different things. We're looking for a drop in oil pressure, a drop in RPM, and an increase in manifold. So he was asking, how does the manifold increase when we bring the prop lever back?
Oh man, you know what? I wouldn't be able to give you an educated answer on that. It's been a long time since I've flown anything with manifold pressure.
I see where we have Sir Spike. Sir Spike, you there?
Yeah, man, I'm here.
All right. I know that perhaps this is something that will be more fresh in your mind. Is something you'd like to take a shot at? Just a clarification for the group.
Sorry, what was I wasn't really paying attention. What was the issue?
Zach, just
Oh.
go over that question for me.
Yeah, so Spike, it basically like we're doing the prop cycle, right? So basically we're looking for the drop in oil pressure, drop in RPM, but the manifold is supposed to increase when we're doing the prop cycle. So I'm asking why.
It's basically because you're putting either more or less pressure on the, I don't want to say the propeller shaft, but that's essentially what you're doing. So basically, if you in a sense change the angle of the blade, as you were saying before, or someone was saying before, that the propeller is going to take a bigger bite out of the air, right? Which means there's more resistance. And if there's more resistance, one of two things have to happen in order for the engine to maintain a particular speed. In essence, it has to either increase manifold pressure to maintain a particular speed, or decrease manifold pressure to vice versa, essentially. Am I being followed or not?
I don't understand how that mechanism can confirm. So
all right, so it's not necessarily controlling it. It's just a situation where the engine wants to maintain a particular speed, and in order for the engine to maintain a particular speed, it has to get more air, right?
Yes.
So essentially, manifold pressure is really just the amount of air you have flowing by a particular joint to get into the cylinders to produce power, in essence, right? So if you want your engine to be spinning at, let's say, 2,000 RPMs, for example, you have to have a particular amount of air going into the engine to produce that amount of combustion to result in that amount of RPM, right? So in essence, what's going on is that because you're putting more pressure on the engine, the engine has to basically pull more air in to maintain the particular speed that it wants to maintain.
But it can do that without me touching the throttle.
Yeah, essentially, yeah. Because remember, you've set the throttle to maintain a particular setting, right?
Mm-hmm.
And you're changing the amount of or you're increasing the amount of pressure on the engine. So in order for the engine to maintain a particular speed, or to get that speed that you want to maintain, it has to do something, right?
Yeah.
Exactly, which is it pulling in more air, basically.
Oh.
Or vice versa.
Right.
That makes sense or not really?
I kind of understand that. That's interesting. Because you said in chat that the prop has nothing to do with the engine. If you change the pitch, it won't affect the engine speed.
Yeah, exactly. And that is the same thing that is going on. The engine speed is not changing. What is changing is the amount of air the engine is pulling in to maintain that speed.
Keep up with the propeller.
Yes. Exactly.
Mm-hmm.
You get the idea?
Yeah, if not, the propeller won't be able to spin at 2,000 RPM.
Exactly. So it's not necessarily that the propeller lever is changing the speed of the engine. It's not. What is going on is that the engine is either pulling more air or not pulling more air to maintain that speed that you set it at, essentially.
And just to clarify, 2,000 RPM is 2,000 rotations of the propeller per minute?
It can be either or. The engine can spin at a particular RPM and the propeller can spin at a particular RPM, or the shaft can spin at a propeller RPM.
Because you could have like a gearbox, right?
Exactly, yeah.
So like, let's say on like a 182, that RPM indication, is it an indication of like the spinning of the crankshaft or what?
I think a 182, I don't remember ever flying a 182, but I mean, it's the same principle, and I would assume it's probably the propeller shaft.
Okay. All right, thank you.
Yeah, right. That kind of make sense-ish? Or, I mean, I don't have a diagram, so
I understand it. I understand it good enough now. Thank you.
Okay, cool.
All right, great. So guys, that was Jason Spike, certified flight instructor. But one thing I want to say is that remember that our discussions are not official ground schools. So what we'd like to encourage all of you to do is that if you want official flight training, just go ahead and visit your nearest flight school to get official training, because these topics and these discussions that we're having are basically only that, just discussions. So that being said, I want to hand back over to Zachary. And thanks again, Spike.
Yeah.
Yeah, no problem,
that
no
was
problem.
that was a good explanation of Spike. Much better than I could have possibly said it. So yeah, so that's basically we're speaking about the governor, and as I mentioned with prop forward and prop back, basically the governor basically does that for you automatically. So if you have that overspeed condition where the engine wants to speed up, then it lets oil out of the prop hub and it increases the pitch angle and it maintains that constant RPM. The same where under speed condition, if you pitch up, let's say on a fixed pitch propeller, where the RPM wants to kind of drop back because of less airflow, then what it does is because of the less centrifugal force, the flyweights, they just end up like coming together like that. And what it does is it brings the speeder springs, apart, like expand, and brings more oil into the prop hub. So basically the same as prop forward and prop back. It's the same principle, just applied to the governor, do it automatically for you to maintain a constant RPM. So that's basically what happens. Everybody understand like the whole concept of constant speed propeller.
Yeah.
Yeah. All right. Cool. Okay. So that was quite a. And now the last thing on a complex airplane is a retractable landing gear. So the primary benefits of being able to retract the landing gear are increased time performance, higher cruise speeds due to the resulting decrease in drag. Retractable landing gear systems may be operated either hydraulically or electrically, or may employ a combination of both two systems. Warning indicators are provided in the flight decks to show the pilot when the wheels are down and locked, and when they're up and locked, or if they are intermediate positions. Systems for each emergency operation are also provided. The complexity of the retractable landing gear system requires that the specific operating procedures be adhered to and that certain operating limitations may not be exceeded. So every different airplane that has a retractable landing gear has their own procedures for the operation of the landing gear, its own speeds at which you can bring it down. What happens if the landing gear fails? Every airplane is different in terms of how they deal with these different situations. So on this next slide, let's have a simple few new V-speeds that would be for people that are just starting to fly retractable landing gear airplanes, which is their like VLO speed, VLO up, VLO down, and VLE. So as I have here with the definition, VLO up is basically that's the maximum speed which you can fly with the gear being retracted. Retracted. VLO down, maximum speed at which you can fly with the gear being extended. And the VLE, maximum speed at which you can fly with the gear being in the extended position. So two of these are basically the same thing in terms of the same airspeed. And the VLO down is what you have to be really mindful about when you're just taking off. So let's say we're taking off in a Seneca and your rotation speed is like 85, 90 knots, and or your VLO down speed is 109. So basically, you need to retract the landing gear before 109 knots in order to safely retract that landing gear. Does that make sense? Anyone?
Yeah.
Yeah. And let's say your VL. So basically before 109 knots, you need to retract that landing gear. And the same with the others, the VLO up. I think I've mixed these two up. Anyway, the same with the VLE. That's the maximum speed at which you can bring that landing gear down. So let's say we're flying at 200 knots. I can't bring that landing gear down at 200 knots. I have to slow down to my landing gear extension speed, which I think was 140, something like that. So you have to slow down to 140 knots before you can bring that gear down safely. All right. So with this whole concept of me always drawing, I have a next drawing to kind of explain how the landing gear system works. this is how it operates, a hydraulically actuated landing gear system. All right, so it starts off with the main thing being the hydraulic reservoir, right? So this is a hydraulic reservoir. All right, so we got some flowing lines here. Okay, those. And then this thing I'm drawing is a pump. These arrows only indicate the direction at which the hydraulic fluid is moving. So let me try to put this up. Can everyone see the screen, right?
Yeah, I can see it.
Cool.
Yep, I can see it.
Just give me a second, let me fill this in. John is too big. All right, so I think everyone can see this. So let me just try to explain real fast what's happening here. So first we have the hydraulic reservoir, which is this thing up here. We have a hydraulic pump. We have something called a shuttle valve. And then we have two cylinders. We have a low pressure cylinder. And a high pressure. All right. And then now in the middle here, we have something called a free fall valve. And again, excuse my penmanship. And then these things right here, these are cylinders for the landing gear. Okay. Does everyone understand so far what everything is? Yeah.
For the most part, everything is clear so far.
All right, so basically, pretty simple situation. You have a hydraulic reservoir. So what happens is you have daily hydraulic fluid in that reservoir. So when you select that gear position, let's say we're in the down, we're on the ground, and we just took off. So what happens when you select that gear position to up, you want that gear to go up. What happens is you have hydraulic fluid that is transported into the high pressure chambers. So yes, you have hydraulic fluids transported into the high pressure chamber. So what happens is you activate this pump, the hydraulic pump. It brings down hydraulic fluid and then it runs through the shuttle valve into the high pressure chamber. So from the high pressure chamber, that fluid now goes to the bottom of each cylinder, right? So when it goes to the bottom of each cylinder, it sends in that high pressure fluid and it forces that gear up. Does that make sense?
Wait, where's the gear?
The gear lever is in the cockpit.
No, not the lever. Where's the wheel?
Oh, the wheels are at the bottom. Because they're on the space, let me try to move down. All right, cool. The wheels are like right here. Yeah.
Okay, thank you.
Yeah. So what happens is that pressure goes into the bottom of the cylinder, and it forces it forces the low pressure out and brings the gear up, right? Because what the main thing I should really explain here is low pressure is connected to the top of each cylinder, right? From the low pressure chamber, and high pressure is connected to the bottom. So it's basically a process of how much high pressure versus low pressure is in the cylinder. You understand?
So
Yeah.
high pressure is doing what to the gears exactly?
So the high pressure retracts the gear, it brings it up, because that high pressure, it goes into the bottom of the cylinder, forcing the low pressure up back into the low pressure chamber and back into the hydraulic reservoir. That makes sense?
Okay, got you.
But
So
how does it bring the gear up though?
It's connected to the.
I'm guessing it would be
because of the
attached
pressure.
to it would be attached to some mechanical linkage that when the pressure is acting upon that mechanical linkage, then it brings the gear up or it brings it down.
Yeah, so basically when you introduce that pressure to the bottom of the cylinder or the top, it is connected mechanically. So we're depending on if it's high or low pressure brings the gear up or down. So if you want to bring the gear down, basically the same process again, you activate the hydraulic pump, and then you get the hydraulic fluid from the reservoir, goes through the shuttle valve into the low pressure chamber, and then that brings that pressure into the top of the cylinder. Again, forcing the high pressure out and back up through the high pressure chamber and bringing the gear down. Does it make sense?
Yeah. I sort of get the picture.
Yeah. So let me draw out the wheels. Yeah. So basically, that's exactly what happens. So basically, when you're bringing the gear up, let's say, that's said, hydraulic pump, that fluid goes down and through into the high pressure, and then it goes to the bottom of the cylinder, and that brings the gear up. And what keeps the gear up, what brings that gear up and keeps it up is clearly the pressure, right? So when you get to, in this specific airplane, let's say the Seneca or the Seminole, 1,800 pounds per square inch, 1,800 psi is what keeps the gear up and in the locked position, and it maintains that pressure to keep it up and locked. Right? So does that explain how the gear comes up and stays up?
Wait, is it,
Right, so
does it go up directly, like vertically?
No. Well, every airplane is different, so it depends on how mechanical it's connected to retract.
Okay, then. All right, thank you.
Does that make sense?
Yeah. Also, can the different wheels be controlled independently, or are they all retracted at the same time?
No, they're all retracted using one lever.
All right, thank you.
Yeah. So that explains what happens when you go in a gear up or gear down position. Now every airplane has different switches basically. So these are like safety features of having a retractable landing gear, right? So every airplane has different switches. So I'm going to just speak on again the Seneca Seminole and what type of switches those planes have. So basically, we have 3 up limit switches. And what the up limit switches do is when the gear is being retracted there is a red light in the airplane, right? It signifies that the gear is in transition. So these 3 up limit switches, all they do is when the gear is retracted, it turns that red light that is blinking off to signify to us that, hey, the gear is up and locked and it's not in transition. Does it make sense?
Yeah.
Yeah.
Yeah. All right. And then again, similarly, we have 3 down limit switches. Right? So the 3 down limit switches, similar to where it turns the light off in the up limit when you're retracting the gear. When you're bringing the gear down, it also turns the light off and says, hey, the gear is down and locked. it also turns on the 3 green lights. So in airplanes that have retractable landing gear, you will usually have 3 green lights to signify that each wheel, the 2 main wheels and the nose wheel is in the down and lock position. So what this down limit switch does, turns off that red light that shows that the gear is in transition. It turns on those 3 green lights, and it turns off the hydraulic pump. Make sense?
Yes.
Yeah. All right. So another one, the high pressure switch. High So all the high pressure switch does, it basically all this does is turns off the reversible pump, the hydraulic pump. When as I said, when you're retracting the landing gear, what keeps the gear up is the pressure. It's 1,800 pounds psi at least in the Seneca. So what it does, it turns off that pump when you get to 1,800 psi, and it maintains that amount of pressure, right? And if there was a situation where you should get less than 400 psi, so if you lose that 1,800 and you get down to 400 psi, it turns that pump on in order to pump more pressure into the gear up. So basically, all these switches are different. They all do different things for the safety of the landing gear. So that's what the high pressure switch does. Do you understand that one?
Yeah, makes sense.
Then you have a gear selector switch. So this is a really simple one. The gear selector switch, all it does, it turns on the hydraulic pump, the reversible pump. So basically, every time you move that gear handle up or down, the gear selector switch is activated. That turns on the hydraulic pump and brings the gear either up or down. That's all that does. And then now we have a flap switch. And all the flap switch does is, if you select 25 or 40 degrees of flaps in the Seneca or Seminole, what it does, it gives you a horn. It's like, it gives you a horn to like signify that, hey, the gear is not down. So when you don't have the gear down and you select 25, 40 degrees of flaps, the airplane thinks you're going to land. So it's letting you know that, hey, the gear is not down. Then we have a throttle switch, right? So the throttle switch, similar to the flap switch, where when you decrease the power in the airplane to less than 14 inches of manifold, it gives you that same horn to signify that you don't have the gear down, because again, the airplane thinks you're going to land, right? And the last switch is the squat. The squat switch, or AKA the weight on wheel switch, or the wall switch. So basically what this squat switch does, it tells the airplane if we're on the ground or not. It prevents you from retracting the landing gear on the ground. Does that make sense?
Yeah, it does.
Yeah.
Are there ever situations, do you know of any situation where that happens?
Personally, no. I'm not sure.
Where a pilot accidentally turns or brings the landing gear up?
No, I don't, because that's the purpose of the squat or the weight on the wheel switch. It just stops you, it breaks the circuit basically. So when you move that gear handle up or down, basically current is not allowed to go to that pump. It stops the current from going to the pump for it to want to retract the landing gear up. You know what I'm saying?
Okay, yeah.
So that's the purpose of that switch. So it's just safety. It prevents you from ever retracting the landing gear on the ground.
Okay.
Even if you move the handle. And with all of that said, that leads to the conclusion of all I have to present on today. Is there any more questions?
I did pose a question in the group where I said there are airplanes with constant speed props and fixed landing gear. Would those airplanes be able to fall under the classification of complex?
Yeah.
So that would still be a complex. So for example, like a 182 that has prop control.
It would be a complex airplane. No?
So as long as it has at least one of the criteria, it's a complex aircraft.
Well, from what I understand, from as long as it has either a constant speed or a retractable landing gear, it's complex.
Okay, thank you.
Because as you may know, most airplanes have flaps. So yeah. Is there any other questions? Not only to me, but to Spike or Demar.
Jaffe, was all of your stuff answered?
Yeah, it was about this topic. Yeah.
Okay. All right. So I don't see any more questions in the chat. Not seeing where anybody is raising their hand or anything like that. So based on that, I'm gonna assume that everybody is good with the presentation thus far, or everybody's all right with it. So that being said, I want to give a thank you to Zach for not only doing today's presentation, but Zach is actually returning for the second time. So just want to thank you, Zach, for passing through once more and putting on a solid presentation on complex airplanes. I really learned a lot as usual. Diagram was really complex, which is ironic because we're discussing complex airplanes, but those were broken down, and it was really a great presentation. So thank you again for that.
Yeah, no problem.
Right. I also want to give a thank you to Demar again, as usual, for always passing through, always giving us the knowledge from a airline pilot's perspective on all of our discussions that we have. Want to thank Sir Spike for passing through as well, and giving his knowledge on complex airplanes and constant speed props and engines. So we